In our previous work on significance tests, we looked at the errors that could be made in the process of carrying out a significance test. And in this video, we're briefly going to have a look at this topic again, but in the context of significance tests using the sample mean. When we carry out a significance test, it may be the case that the null hypothesis is true and the significance test concludes that there is not sufficient evidence to reject the null hypothesis in favour of the alternative hypothesis. In which case, if you like, the significance test has decided to accept the null hypothesis. And if that is the case, then the significance test has given us the correct answer. We could, on the other hand, be in the position where the alternative hypothesis is in fact true, and the significance test concludes that there is evidence to reject the null hypothesis in favour of the alternative hypothesis. In other words, we're accepting the alternative hypothesis, and that again means that the significance test has given us the correct answer. Our third possibility is that the null hypothesis is in fact true, but the significance test concludes there is evidence to reject the null hypothesis in favour of the alternative hypothesis. And if that happens, we've clearly made a mistake. So the significance test has given us the wrong conclusion. And the procedure involved with the significance test means that the chances of making this mistake are small and in fact are the significance level of the test. This type of error is called a type 1 error. And a type 1 error is the mistake of accepting the alternative hypothesis when the null hypothesis is in fact true. This will happen when the value of the test statistic lies in the critical region, and the probability of this happening is the exact significance level of the test. The other way in which we can make a mistake is if the alternative hypothesis is in fact true, but the significance test concludes that there is not sufficient evidence to reject the null hypothesis in favour of the alternative hypothesis, so we end up accepting the null hypothesis, in which case we have made the mistake of accepting the null hypothesis when the alternative hypothesis is in fact true, which is an incorrect conclusion. In order to minimize the chance of making a type 1 error, this second type of error may have quite a large probability of happening. So a type 2 error then is the mistake of accepting the null hypothesis when the alternative hypothesis is in fact true, and we need to realise that the probability of making such an error is difficult to work out unless we know exactly how the alternative hypothesis is true. And we also need to realise that the probability of a type 2 error may be quite high. So let's have a look at this in terms of an example. The IQs of 16-year-old pupils are known to be normally distributed with a mean of 100 and a standard deviation of 15. A random sample of 20 16-year-old pupils from a school gave a sample mean of 106.2. We want to determine whether this gives significant evidence at the 5% level that the school's 16-year-old pupils are brighter than average. We want to describe the mistake that might have been made in making this conclusion and give the probability of making this mistake. And then finally, we've got to suppose that the significance test is used in a school where the mean IQ of all the 16-year-old pupils is actually 108. We've got to find the probability of making a type 2 error if the significance test was used at this particular school. So we need to set up our significance test first of all, and the first thing we must do is define the variable that we're going to be considering, which in this case is the mean IQ of 16-year-old pupils at this particular school. We don't know what the value of mu is, but what we are trying to do is we're trying to decide between two possible explanations. The first one being that the school is no different from the national figures of 100 for the mean value, and the alternative hypothesis is that the school's pupils are brighter than the normal, in other words that mu is greater than 100. The test statistic for our significance test is the mean IQ of a random sample of 20 16-year-olds at this particular school. If the null hypothesis is true, then we can say that the sample mean is normally distributed with a mean of 100 and a variance of sigma squared over n, so that in this case is 15 squared divided by 20. The test that we are going to conduct is a 5% one-tail test. So we now need to find the critical region for the test. Now the critical region of the test is going to be a right-hand tail. So its critical region is going to be the sample mean is bigger than C, where the probability that x bar is greater than C is equal to 0.05 if the null hypothesis is valid. As usual, we need to turn this into a left-hand tail condition. So that becomes the probability the sample mean is less than C, has got to be 0.95. And then we can use the inverse normal functions on our calculator to determine that C is 105.52. So our critical region is x, the sample mean is greater than 105.52. So our decision rule is that if the sample mean is greater than 105.52, then there is significant evidence to reject the null hypothesis in favour of accepting the alternative hypothesis. Otherwise, there is not enough evidence to reject the null hypothesis in favour of the alternative hypothesis. Well, we had x bar, the sample mean, being 106.2. This is in the critical region, so there is significant evidence at the 5% level that the mean IQ of 16-year-old pupils at the school is higher than 100. The mistake that we might have made in deciding to accept the alternative hypothesis is that the null hypothesis might actually be true. So, the fact that we've decided to accept the alternative hypothesis means it says that it's still possible that the null hypothesis is true. So it is possible that we have accepted the alternative hypothesis when the null hypothesis is true, and that is a type 1 error. And the probability of making this error is the significance level of the test, which in this case is 5%, or as a probability 0.05. If the significance test was used in a school where the mean IQ of all of the 16-year-olds is 108, then the probability of making a type 2 error in the test is the probability that we accept the null hypothesis when the alternative hypothesis is true. Now we will accept the null hypothesis if the value of the sample mean is not in the critical region. So we will accept the null hypothesis if the value of x bar is less than 105.52 when the alternative hypothesis is true. Now what have they told me? They've told me that the alternative hypothesis is true because the mean in this second school is 108. The mean IQ in this second school is 108. And that means that the distribution of the sample mean is not normal with a mean of 100 and a variance of 15 squared over 20. It's actually got a distribution which is normal with mean of 108 and a variance of 15 squared over 20. So what I want to do is I need to work out the probability that x bar is less than 105.52 given that x bar is in fact normally distributed with a mean of 108 and a variance of 15 squared divided by 20. I can use the probability functions for the normal distribution on my calculator to obtain that as being 0.23. So there's a 23% chance that the significance test will end up making a mistake if it's used in this second school. Now to finish the work on this video, what I'd just like you to have a go at is this one question here. Have a go at it. So you're setting up a significance test, you're looking at the possible errors that can be made on this significance test, and finally you've got to just have a think about the choice of sample for the test. So have a go at this question and take along your solution to your next lesson. So that concludes our look at errors with significance tests.